Okay, so let's find, we're going to do the simplest example I can think of to start. Find the power series solution. To y prime minus y equals 0. So we know what the answer is. Like this is y prime equals y, a function who is its own derivative. We know it's going to be y equals c e to the x. That's what our answer is going to be. You may recall that the Taylor series, the power series expansion of e to the x, is n equals 0 to infinity, x to the n over n factorial. That's what we're going to get. Okay, and we're going to expand this. We're going to find this power series at x equals 0. That's an ordinary point here. So my guy in front is a 1. That's defined everywhere. That doesn't have no place where that equals 0, no place, I mean, it's just 1. So I can find the power series anywhere. For simplicity, I'm going to do it at 0. So we assume our solution looks like this. Our goal is to find all the ANs, find all the coefficients. Once we found all the coefficients, we're done. So I need to plug that into the DE. I need to take the derivative. Now, because this function is analytic, I'm allowed to pass a derivative inside the sum. The derivative of the sum is the sum of the derivatives. I can bring the derivative inside and just take the derivative term by term. So the derivative, that's a constant, derivative of a sub n x to the n will be an times n x to the n minus 1. Now notice here, we won't do this on all the problems, but I think it'll be helpful on this one. Notice my very first term. Let's write out some of these just for fun. So I'm going to plug in n equals 0. I'm going to get a0 times 0 times x to the negative 1 if I plug in 0. Plus, plug in 1. a1 times 1 times x to the 0 plus a2 times 2 times x to the 1 and so forth. This first term, that's not a power series first off. That bothers me that I've got an x to a negative power. That will never happen. We'll always have positive powers, but it doesn't matter because it was 0 anyway. 0 times anything is 0. This function was analytic at x equals 0, so I don't have to worry about this. This part doesn't even exist because I've multiplied it by 0. So the first term was 0. Which means I don't have to start my count at 0. The first term was 0. I can, if I want to, just wait until 1. Start counting at 1. So I'm going to rewrite this sum as 1 to infinity, because the first one was 0. Now I'm going to plug, oh, that's n minus 1 right there. I'm going to plug that in here, and I'm going to plug this in right there. So I'm going to need the space. That says the sum from n equals 1 to infinity of a sub n times n x to the n minus 1 minus the sum n equals 0 to infinity an x to the n must equal 0. That's what the equation says. I need to squish these together. Now I could write out a bunch of terms. There's nothing wrong with that. I could write out a bunch of terms here and just match pieces up. Like n equals 1 here. The first one is a1 times 1 x to the 0. This guy, his first term. Again, because everything's analytic, I can distribute this negative and do this one term at a time. This says a0 x to the 0. The only way an entire power series can equal 0 is if every term equals 0. So this must equal 0, which says that'll tell me a1 minus a0 equals 0. So I could do that term by term by term, but it's easier if we can just squish these together and write this as one single sum. Well, in order to do that, I need the powers to match up. And I need them to start at the same place. There's always two things we have to match. The powers have to match, and the starting point has to match. Sometimes we can just play a little game and force that to happen. Other times we have to break off extra pieces and force that to happen. So here we're going to play this game. I'm going to call k n minus 1 because I want these to look the same. That's just a symbol. There's no plus 1, minus 1. That's just an n. I'm going to force this guy to be a k by doing this substitution. That's the same as saying n is k plus 1. I'm going to replace all my n's here in terms of k's. This sum will become n equals 1 would be k equals 0. N is k plus 1. N is k plus 1. N minus 1 is what I called k. And then I've got this other sum. Okay, now, whenever I write out a sum, the letter I choose for my index is completely arbitrary. It doesn't matter. I've chosen to call these n's and these k's, but I could replace them all with i's. I could rewrite this guy if I wanted to. Sum I equals 0 to infinity, ai x to the I. It's the same sum. This is just an index. It doesn't matter what letter I use. And I could replace all these k's with i's if I wanted to. But that seems like a lot of extra writing. Why don't we just replace all these k's here that we have with n's, since we already have n's here? Now that's going to bother you because right here I made this substitution. And now I'm going to undo. I'm going to ignore what I did there. And I'm just going to say, you know what, forget all that. I'm just going to replace k's with n's now. And that might bother you at first. It did me. I was like, you can't do that. Sure you can, because it doesn't matter. It's still the same sum. Write out several terms of this. Write out several terms of that. And they are literally the same thing. It doesn't matter what letter you use. So I'm going to, instead of calling these k's, call them n's. And get this equation. Now, all this stuff I went through right here, there's a way to skip over that. There's a shortcut. And that shortcut is to look at this guy and go, look, I need this to go up by 1 to match that. I need this to increase by 1. So everything here needs to increase by 1. The way to do that without changing the sum is to decrease this guy by 1. Make these all go up by 1. Make him go down by 1. Look, that's what happened. Went up by 1, went up by 1, went up by 1, went down by 1. Now my starting points are the same. I started n equals 0 on both, and my powers, this is an x. My powers are the same. That's the important part. So I need the space here. I'm going to come back, rewrite that line. So I have the sum n equals 0 to infinity, a n plus 1 times n plus 1 x to the n minus sum n equals 0 to infinity, a n x to the n equals 0. Now I can squish the sums together into one single sum. I have to make these match and these match before I can do that. 1 times n plus 1 minus a n times x to the n equals 0. Okay, so we have this power series. This is a single power series now that I claim equals 0 for every value of x. That's what this says. This says that this entire power series, you plug in x equals 100, you get 0. You plug in x equals 45, you get 0. The only way a power series can equal 0 for every value of x is if every single coefficient equals 0. So if the sum bn x to the n equals 0, that implies every b is 0. That means this stuff here must equal 0. Which means if I move this an, we always want to solve this for the higher subscript. This says a n plus 1 will be a n divided by n plus 1. This is called a recursive formula. And we're always going to get a recursive formula. We're always going to find higher order terms, higher order coefficients in terms of lower order ones. We're going to use this to generate a bunch of our terms. Hopefully we see a pattern and we can write down what we think the general term is. But we won't always be able to. Sometimes we'll just write out 5 or 6 terms and go, well, I hope that's enough. In this case, we're going to easily see what the pattern is and figure out what the general formula is for an. Okay, so I'm going to write that above here. So my recursive formula was an plus 1 equals an over n plus 1. This was a first order DE, first derivative. So your first guy is always going to be free. A0 is always free. That's going to be our constant of integration. That's like our C that we get when we integrate. If this were fourth order, we would have 4 free. The first 4 would be free. There's no way to determine them. You have to solve an initial value problem to solve them. So first order, we get 1 free. If this were double prime, we would have 2 free. Right, now I'm going to use this formula, start plugging in values for n equals 0. N equals 1. Start plugging in values for n to find successive a's. So a naught is free. When I plug in a 0 here, I'll get a sub 0 plus 1 equals a0 over 0 plus 1. I just plugged in a 0 for all the n's. That tells me a1, the next one, is equal to a0 divided by 1. Same thing we got if we had done it term by term. Plug in a 1. So we do it a little quicker now. A2 would be A1, n equals 1, over 1 plus 1, 2. But wait a minute, I know what A1 is. I just wrote it. It's right here. So that's A0 over 2. Every single term here is going to be in terms of the free ones. Since I only have one free one, every single coefficient is going to be some multiple of A0. If I had 3 free ones, it would be every coefficient would be a combination of those 3 free ones. Plug in n equals 2. So A3 would be, I'm plugging in n equals 2, A2 over 2 plus 1 is 3, but I know A2, that's A0, so that's A0 over 3 times 2. Equals 3. Notice, by the way, this used to get me when I used to do this. When I'm doing n equals 2, I'm not finding the second term. I'm not finding A2. I used to get this in my head that when I write this down here, that I'm finding A2 because I said n equals 2. But no, I'm not. Look, at n equals 2, I found A3. This thing that you've written here does not tell you which A you're finding. This tells you which A you're finding. So n equals 3. I'm not finding the third term. I'm going to find 3 plus 1, the fourth term. That will be the previous one. n equals 3 over 4. So that's A0 over 4 times 3 times 2 times 1. We're starting to see a pattern here. Every time I go up to the next term, I multiply by the next number. So this is A0 over 2 factorial. That's A0 over 3 factorial. That's A0 over 4 factorial, and so forth. Okay, so we're starting to see a pattern. So y, my function, is going to be, remember, it's the sum n equals 0 to infinity an x to the n. These two will always match. So my first one is always going to be A0 every single time. X to the 0 was 1 plus A1. A0 over 1 factorial plus A2. Oh, forgot my x. X to the first. A2 was A0 over 2 factorial times x squared. A3 will be times x cubed. And I'm noticing a pattern here. This is the sum. This keeps going on forever. If we didn't notice a pattern, we'd write out 4 or 5 of them and be done, and we'd say that's it. We'd be happy. But we do notice a pattern here. I could say, this looks to me like I'm going from 0 to infinity. I've got this A. I could pull that A out in front, A0. That looks like that's the sum of x to the n over n factorial. Wait a minute, I know what that power series is because I took Calc 2. That's e to the x. There's my solution, e to the x. Because we happen to recognize this formula we came up with. Sometimes that happens, sometimes it doesn't. Okay, now if we wanted to say we didn't realize this. By the way, you know what your calculator does when you type in e to the x? It uses this formula. Your calculator doesn't have doesn't know how to do e to the x, it just does a power series. If I wanted to approximate this function near zero, remember I expanded this at the ordinary point x equals 0. So if I wanted to approximate it at, say, 0.1, then I would just plug in 0.1 for all the x's, and I would go as far as I think I needed to get a good approximation. Maybe write out 10 terms, plug in 0.1 into all of them, and I would get a good approximation. Yeah, that's what your calculator does.